the main thing we're kind of tackling now, we did twist last time, and this is going to apply to twist as well. But we're going to talk about, what happens if you don't have enough information, which is what this introduction is. And then we're going to look at what about weird shapes. I don't know if you noticed it, but everything we're twisting is like a cylinder every time. And that's actually often the case. They're a way smarter shape. And I'll show you an example of that in just a minute. They're the best shape. They're easy to build and they're stronger than like a triangular tube or a hollow tube or something like that. But we're going to play with that because those are kind of options. So let's see if we can get our mind around this dude. So statically indeterminate, remember, means basically this idea that if I come in here and say, oh, okay, this thing is pinned between a couple of walls. And so because it's pinned against the wall and I can see that 500 Newton meters is coming toward me, then that means the wall would have to be resisting that kind of in the opposite direction. Does that make sense? So that'd be the torque at B, I guess, in the opposite direction. And then the same thing would be true over here. That'd be the torque at A in the opposite direction. And so in order for this thing to, have any twist in it, then those torques would all have to match, right? Because remember, it's just going to rotate if they don't all equal 0. So, and then the other thing to notice is, notice I don't like what's positive and what's negative, because this is 3-dimensional. It's kind of hard to determine that. In a sense, it doesn't matter. To keep it simple, I could just say, well, since torque A and torque B are working together, then wouldn't that be torque A plus torque B? And then I could say, well, that would have to equal the 500 Newton meters. I mean, I could say torque A plus torque B minus 500 equals 0. That's kind of the more normal way to write, well, static equations. So if that's true, then there actually will be twist on the pipe. However, do you agree that this is static in the sense that it's not moving? And then it's actually undetermined what torques would have to be there, because there's lots of numbers that add up to 500. So remember, we had the same discussion before when we had a pipe pinned between a couple of walls. And at that time, we were talking about axial loads. And we said, well, yeah, if I push on that or pull on that, it's going to want to get longer, but then it's pinned and it won't get longer. Well, the same thing is true here. Although you look at that and think that can't be solved, the fact that it's actually pinned on both sides, that actually means that it can be solved. And so let's kind of play with this and see how that might work. I stole these figures out of the book. I don't know why that little cut tool I use leaves a stupid image around it. Now, since it's pinned, since it is pinned to the wall, does it make sense then that the twist, which remember we had labeled B, is actually got to be nothing? It isn't going to twist. Well, at least not against the wall. Now you may realize it can twist in the middle. Does it make sense that if you grab the middle and twisted it, it would twist in the middle, but the twist relative from A to B? So I should say maybe more particularly the twist from A all the way to B would equal 0. But if I labeled this point in the middle, C, as they labeled it up there, does it make sense that the twist from A to C is not going to be 0? So what is that? And neither is the twist from C to B. However, the twist from A to C is going to have to equal the twist from C to B in order for this to be true, right? That's kind of the idea. If the twist from A to B, end to end, because the two ends aren't pinned, and again, as I said before, imagine this is like, hey, let's put a little line like on the top of that pipe there, and let's put a little line on the top of this pipe here, and now go 500 on it. If you go 500 on it, those two lines aren't moving. But is this line in the middle going to move? Yeah, it's going to move. It's going to go around that way a little bit. So do you see what I'm saying? The twist from A to C, that's going to have some twist. The twist from C to B is going to have some twist, but does it make sense to actually have to be equal in order for the twist from AC to be nothing? They have to be exactly the same. Okay, well, that's the key to the second equation then. So the fact, like before, that I'm looking at this saying, okay, great, that's true, but that's an equation with two unknowns. Well, here's my second equation with two unknowns. Recall that twist on your note sheet is equal to the torque times the length divided by the resistant power that a circular object has to twist. And it's kind of rotational. Is that what it was? It's rotational moment, no, not moment of inertia. Modulus of elasticity. So cool. Well, then let's just find the twist of AC and the twist of CB and set them equal to each other. Now, this is where the section part comes in. It's really important. Do you agree that everywhere in here, the twist is A all the way across here as I section that thing up? Now, as soon as you get to 500, it changes. But until you get to 500, it's just twist of A all the way across that thing. Just like we said when it was a normal force pushing into the end, we said, oh yeah, every part in that 3 meters, if this is 100 pounds of force out here, then every single part in this is also going to be pushing back 100 pounds in order for it to actually be static, in order for it not to move. And if it doesn't move, then it actually will change size. Well, the same thing is true here. It's twist of A all the way through that thing. So in that section right there, I would say the twist from A to C would be the torque there, which is the torque at A, times its length, which we were told was 3 meters. And I'm going to do something kind of cool here, which is to say divided by JG. In other words, I'm not going to look those up. Now, in this case, I don't have a choice because it didn't even tell me anything about them, but we'll just watch this. It's kind of interesting. And then on the other side, I got a choice on the other side. Would you agree that I could call this section right here torque of A, but then because in a sense, I was calling that positive. Then when I got to 500, does it make sense? I'd have to say, oh, okay, this section is torque of A minus 500 then. Or I could just call it torque of B. Since I could look at this side and say, oh yeah, look, it's torque of B everywhere across there. So I could call it one of two things. I could call it anything I want. I'll just call it torque of B. Torque of B times 2 meters, also divided by those two. Oh, look, they actually cancel out. That's why I didn't bother to write them in there. So had I looked them up, it's kind of like, oh, I didn't really need them. Caesar likes that. He's likes gets those done first. Good quality. So does it make sense? There's my second equation. So now I have two equations, two unknowns. Ah, two equations and two unknowns. And so if I solve those two, I end up with torque at A is 200 and torque of B is 300. So you actually can determine it, Newton meters and so forth. So we're gonna have to use that principle. So to me, the backbone of this is kind of that second formula right there. If it's pinned on both sides, there isn't going to be any twist overall. Now, if you went back, just to kind of highlight this, if you went back and said, oh, sweet, torque of A is 200. If I put 200 in here, and this is 3, and then J is some number, and then G is some number, it's not like that's 0. Does that make sense? It's not saying that's 0. There is a twist from A to C. It's just that it's going to be the same. And if I put 300 in here and you had the same values, then these are actually going to be equal. So overall, there's no twist as far as the ends are concerned, but there actually is in the middle. So, okay, cool. Well, armed with that, let's see if we can get problem numero uno right. To be that guy. So first glance, you should say, oh yeah, cool, that's the same setup, except for, well, there's two different kind of forces in the middle. And unfortunately, does it make sense that's actually 3 different twists in there instead of just 2? So I will have a twist from A to C. I will have a twist from C to D. I will have a twist from D to B, but all of those added up is going to be nothing because A to B is going to be nothing, right? And maybe one even twists, clockwise and one twists counterclockwise. I don't really know. But let's kind of section those. So again, notice both of these twists, if you will, are kind of coming toward us. So does it make sense by logic that these have to be going in the opposite direction? Same as it was a second ago. Just logically. Again, if I screwed that up and wrote them the opposite direction, I would just get negative answers instead of positive answers. Those have to work together, and then maybe you can see it's going to be a little tougher. I can see those have to add up to 700. Since 200 and 500 is 700 go one way, then those two also have to add up to 700. So I can kind of see that. Torque A plus. So that's going to cause everything to be static. And therefore it will actually twist. So there's kind of my first equation. Now let's see if we can work our way into this. So for no particular reason, do you agree that all of the twist in this section is twist of A? And so I'm just going to call that positive out of laziness, I guess. So then the 500 would be negative. And when I reach the 500, does it make sense it'd be twist of A, but then it'd be minus 500? Since I don't know what twist of A is, I can't actually determine that. But does that seem familiar? Previously, you actually knew all the twists and you just added them and got answers. And then this next one would be another 200. So does it make sense this one would jump up to twist minus, or I'm sorry, torque at A minus 700 now?
So could you do all this without two equations?
Yeah, that's exactly right. And so I'm going to do this one without two equations. I'm going to get twist of A just from that setup right there, and I'll just know twist of A. Now, I'll still need this equation because once I know twist of A, that'll tell me how to get twist of B. So I don't have to start over. So if twist of A comes out 600, then I'll go, oh, twist of B is 100. Good. I got them both now.
All those added together have to equal 0.
That's exactly right. So if I take all those and add them, each one individually is not 0, but if I add them all together, they'll be equal to 0. That's just another way to look at it. Now, a second ago, I said those two twists are equal to each other, but here, because I have 3, it's kind of hard to set them equal to each other. Does that make sense? I just have to add them all up and they got to be 0. I could have done that a minute ago. I could have said the twist of this one plus the twist of the next one will equal 0. And because one of them was negative, then they would have just been those equal to each other. But this is probably just an easier way to approach it. And I won't even have 2 unknowns. Great. Well, I have all those torques and I have all these lengths down here and I've got JG. Do I need to know JG? I don't know. Let's think about that. It sort of seems like they're thinking I do, because notice they told me what kind of material it is, and then they also told me the size. So it seems like they think I should know it, but part of me is like, well, I didn't need to know it a minute ago. Do I need to know it? Let's write it out. So the twist all the way from A to B. So for the first section, torque of A times its distance of 1 meter divided by JG plus the torque here is torque of A minus 500. And notice I need parentheses there, times its distance of 1.5 meters divided by JG plus the torque of A minus 700 times its distance, which is back to 1 meter divided by JG. That total twist has to be equal to 0. Do I need to go look up J and G? Yeah, does it make sense I can because every fraction there is divided by JG, does it make sense I can multiply both sides by JG and it'll be gone? So I don't need to look them up. If I did look them up, they're still just going to disappear, but I guess I actually don't. So that means T torque at A, and I'll go ahead and multiply this out, like distribute 1.5 plus 1.5 torque of A, 1.5 500s is 750, so that's minus 750, plus another torque of A minus 700. All that has to be 0. I'm happier with that equation because it's only got one unknown. So that looks like a total of 3.5 torque of A's. And that's 1450 on the other side. So if I divide 1450 by 3.5, I get, unfortunately, not a very clean number. I get torque of A is approximately 414.3. Again, I'm being a little lazy here. Let's see, let's look back at all the units. Whew, I got lucky. Do you notice those distances were in meters? And the torques were in Newton meters. So everything was newtons and meters. And so I got kind of lucky. So my torque is going to be Newton meters, but so my laziness didn't hurt me that time. So I found that. And now because 414 plus the torque of B has to be 700, I can plug that into this first equation we said. And then I also know torque of B, which is 285.7. Or however you choose to round it. Now, does that make sense? Stare at the picture. I always like to ask that question. Does it make sense that A is working harder than B? It does, because it's got 500 next to it, right? 500's torquing pretty hard over there by A, whereas it's only 200 over there by B. So yeah, of course A is working harder. That's kind of cool. Makes sense. Doesn't mean I'm right, but at least it makes sense. Now, I want to draw a picture of something here because it actually asks something rather interesting. Notice it asked for the absolute maximum shear stress. It didn't actually ask for the two torques. Like in the previous, intro question I showed you a minute ago, we just said, hey, look, we actually found those two torques. We're done. But remember, in the real world, what you need to know is how much stress does that actually put on the pipe itself, like my fork that just broke over there. Is it going to break? And notice I don't need to know all the stresses. I just need to know the biggest one. So that's kind of cool that they said, what's the absolute maximum stress? To Caesar's point earlier, could you make actually each of those three lengths out of a totally different kind of steel? Yes. Would it cost a lot of money to weld them together and get three different kinds in? Yes. Would it look weird? Yes. So it's probably going to be all the same. But we also have to design for the worst case scenario. Now, what do I use for my torque then? I have 500, I have 200, I have 414, and I have 285, right? But let's stare at this for just a second. So a minute ago, I labeled all of these, did I not? Although the 500 is sitting there, this is T of A, this is T of A minus 500, this is T of A minus 700. Isn't that the three torques? Yeah. It's not four torques, 414, 285, 500, and 200. If I thought that, then I'd say, oh, 500 is my biggest one. But 500 is not happening. It's happening right at that point, but it has other torques around it. Does that make sense? Go ahead.
Well, the last one, the TA minus 700, is the TB.
Yeah, that's exactly right. So that last one, I could have actually used TB there. Now, I'll tell you, there's a little conundrum in my mind that's just driving me insane, and I haven't figured it out yet. If you replace this right here with TB, and that should make sense because it's like you're just, if I started this not from left to right, but from right to left, does it make sense? All the equations would have been made out of TBs all the way across. So it seems totally logical to me that that would be TB. And so this equation right here that I wrote could have had, a TB right here instead. And then I would have just had two equations, two unknowns that got the same answer. Bad news, you don't actually get the same answer. You get the same answer if this is negative TB. Now, this makes sense if you look at this equation right here, because what is TA minus 700 according to that equation? It's negative TB. However, that doesn't look right in the picture. Didn't I just get done saying that this was like positive going that direction? And yet over here, it's like, isn't TB positive? Like I want to call that TB. My only guess on this is it has something to do with the sign convention thing that we have that's came up a few times in class. It's kind of like, well, I'm looking at this shaft from this side and I'm calling that positive. But then if I look at it from the other side, all of a sudden that's not counterclockwise, like, oh, it was clockwise, but then you look at it from the other side, oh, that's counterclockwise now. So it's, I think it has something to do with that, but that's bugging me. Because I got this wrong first time I was doing it. I thought, oh, I'll just call that TB, two equations, two unknowns. Didn't get the answer in the back. What? And I did realize eventually it kind of contradicted that equation right there, but I was just like, what? Logically, that's just bugging me. Am I right about that, by the way? If I look at it from this side and I say that way is going to be positive, and see, that's counterclockwise for me, the way I'm looking at this right now. But then it's clockwise for you. Maybe that is it. Maybe that's the reason right
We
there.
got the home view and the other view.
Exactly,
What's that?
right.
View.
Maybe that's it. And the times that sign conventions have come up, this is the reason, because it kind of screws everything up. And the weird thing is because like you really do get totally different numerical answers there. And it just feels like, wow, how would you catch that kind of mistake? And so somebody says, all right, here's the sign conventions for stuff like that. Oh, okay, I see maybe why that's important now. Again, I did not know that 2 seconds ago. I don't even know if that's the right answer, but I think it is. Okay, so for that reason, I want you to watch this. If I go back to these three equations up here and I put in TA, which is 414, does it make sense? The first section is 414, but what's that next section from C to D? It's 414 minus 500, which is actually like 85 or something. And what's that last section? 414 minus 700. And so there's not 4 torques here. So I'm going to actually draw kind of a diagram of this really quick, just so you think about this, because I also found this confusing and eventually figured it out. So let's see, this thing went from A to C to D to B. So this is A, try to draw it at least roughly to scale, to C, and then B. D was pretty big. And then B was about the same size as on the other side. So it looks something like this. So we're 414 all the way from A to C. You agree with that? I'll just round it off. We're 414. The second section, 414 minus 500, that's 86. Not only that, it's negative 86, isn't it? So it suddenly jumps down here to negative 86. And it stays negative 86 all the way through to D. And then if I take 414 minus 700, now it's negative 286. So it actually jumps in this direction, not in the direction that I thought. So does it make sense that of those 3 torques there, 414 is actually the biggest one? I don't think that's obvious. You agree with that? That's not obvious. You kind of have to almost draw this out a little bit to kind of see that, I guess. Okay, if that's the case, I can actually find, remember this was called the shear stress, tau, the shear stress in the shaft. I don't know about you, but it's like, wait, what was that equation again? Yeah, torque times outer radius divided by J, divided by the rotational resistance to torque. So I say, cool, I know that this is 414.3. I'm going to put units in it this time just to see if that matters. I can't remember. C was the outer radius. Oh, I do need that 60 millimeters. Let's see. Oh, that's millimeters. Maybe I better be in meters. So that's, oh, and that's a diameter, right? You're going to be careful there because that C was a radius. So that's 30 millimeter radius, which makes it 0.03 meters. So I'm just going to make a note here. That was a radius, and that shows on your note sheet because it's not easy to keep straight. And then J for a solid shaft was pi over 2 times that radius to the fourth. That was our formula for that. That's for a solid shaft. So again, I'm looking at this thinking, okay, I got 2 meters on the top, I got 4 meters on the bottom. So there'll be newtons left on the top. And square meters, oh, that's right, newtons per square meter. That's like the PSI. Okay, that's right. That makes sense why that's shear stress. That was a pound PSI kind of number, newtons per square meter or pascals. Awesome, cool. Okay, so that's kind of cool that I stuck those in there. So it was important actually that I was in meters. Otherwise, those wouldn't have canceled out like that. So I got kind of lucky there. So pump that all into the machine and you get 9768. 9768247. Which of course is going to be move the decimal point 36. It's going to be 9.77 megapascals. That's probably what I would see in the back. Do you agree with that? 9.77 mega, 6 decimal places, megapascals. As far as tests are concerned, I don't care. So now I know which kind of material to pick, right? I don't think I'll take the time to do this because it seemed like that was one of the numbers that we didn't find on that chart, but notice I never needed to know what that was. But they're saying they chose A992 steel, so apparently that has the capacity to resist that. Let's go look again and satisfy ourselves that it's not on the sheet. I think this was that one thing before that wasn't there. Does it have a, is that right? Do you remember that? Metric. Yield strength, megapascals, shear, is that it? Ultimate stress, megapascals, shear. Looks like there's numbers there. A992 steel. It's the second one down in this white column here. There's nothing. Like they didn't, I don't know why. There's nothing there. So I was a little excited for a second, but what would I want to see? If there was a number there, what would I want to see based on what we just did? Some number bigger than that answer we just got, because that's what's going to happen to it, right? So we're going to have a number bigger than that. Otherwise, we're going to break, right? Kind of cool, huh? You see how close we are to like being able to pick stuff? All we got to do is look it up in a chart now.
Not our maximum stress, it would be smaller.
That is the most stress. So we have to have something that's capable of that or even more. So the material strength needs to be more than that.
Oh, I
See what I'm saying?
Yeah.
So there's a couple tricky things in there that, as I said, embarrassingly, I missed this for a while until I kind of got my mind around it. I'm giving you the explanations that occurred to me, so you're probably not going to miss it, but even the textbook wasn't really helpful. It just shows here's how you do it. And why? Doesn't do me any good. Let's take a look at another question similar to that, because it asks it slightly different in a different way, and also just because we need a little bit of practice, but I'll go kind of fast here. So this is a little nicer because it doesn't have as many torques in it. So it's going one way. So again, I'm going to send my torque at A in the other direction. And I don't like kilonewton meters, so I'm going to call this 2000 Newton meters. And so because T of A is going one way and that's going the other way, then we know B is kind of working its way in this direction as well. Then we say, okay, that'd be T of A minus 2000. So that's what's going on in here. That's the torque in there. The torque in here is just the torque of A. Again, sections and so forth. And so it's So it's like, okay, cool, I get that. So true to what we just said a second ago, then I can say, okay, cool, then what's the twist from A to B? Well, it'd be the torque of A times its distance, 800 millimeters. Again, I'm wondering, should I change it? I'm thinking, yeah, that's 0.8 meters. I think I'll call it 0.8. Can I get away with JG just being JG again? So there's the twist from A to C. Maybe I'll write that in here. This is the twist from A to C. And then I'm going to add that to the next twist, except for the next twist has a different torque. It's torque minus 2000 because that 2000 is working against it. And it's a different distance, 0.6 meters. I'm leaving the units off, 0.6 meters, also divided by JG. And so that's the twist from C to B. But what I know is that has got to be equal to 0 since there is no twist. And like last time, oh, I actually don't need to know JG again. Those go away. So that's kind of cool. I won't take the time to, to solve that equation, but that tells us that twist of A is 857. I'll just leave it at 857. No, I better not. 857.14 Newton meters. So I know how much torque is actually required at A. And remember, that's not a guarantee. You're going to put some bolts in the wall. Could those bolts shear off? Could they pull out of the wall? That's why you need to know that number. Just saying it's pinned doesn't mean it's pinned. You're the ones that have to make that happen. How do I get torque of B? Well, this is where I do need that second equation. I have to say that, and I'll write it out more traditionally this time. Torque of A is positive minus 2000 plus torque of B has to be equal to 0. So that it actually does twist, static. So then I plug 857 into that and I get torque of B is 1142.86. So the statically indeterminate, what looked to be statically indeterminate, impossible to determine how much A and B is not, thanks to the fact that we know that the sum of all the twisting from A to B is 0.
So torque is force times lever on distance. So
Nice.
this truly is twist on, because like it seems like our twist is higher the closer it is to the side. So it's closer to B, 600 millimeters to 800, and that's why its twist is 1142.
Well, that's torque, not twist.
So
Twist
then
is B. So
Why
they're-
is the torque higher the shorter?
Yeah, good job. That actually contradicts. No, that doesn't. That agrees. So because the 2000 is closer to B, it's going to put more torque on B than it is on A because of the twist that's over there. That's exactly right. It won't twist as much, therefore it'll torque more. So it's closer. I mean, I
Right.
think it was just closer. It's closer. So B is going to have to take more than A will, since it's closer to that.
But if you go for force times lever arm distance, you would think that T of A, because it's further, the lever arm distance is greater. That's why I'm like trying to, in my head, I'm like, maybe I
Yeah.
should think about this as a different force.
Well, the 600 is not the lever arm distance. If you were actually going to say force times lever arm distance, you'd actually have to kind of think of this as like the force right here. And the lever arm distance right there would be like 3. Force times 3 is 2000. Like that's how you would find the torque if you were told the force. We were just told the torque. 2000. Oh, okay, good. I just have the torque. Must be some chain hooked to it, torquing on it, and they're just telling me, and I didn't have to figure it out myself.
And we're measuring.
Yeah. And so the fact that if I have a mark on the top of this tube right here and I put a mark on the top of that tube right there, those two are going to stay in that orientation. Now, the mark in the middle here is going to go that way. It's going to move. The twist from A to B is going to be 0. That does not mean these two twists, these two individual twists right here are not equal to 0, but does it make sense they have to be equal to each other in order to add them? Like one could be -7, one could be +7. Let's see. So what did they ask? Determine the maximum shear stress in regions AC and CB. So this time they just said, tell me both of them. They didn't say what the maximum was. They just said, tell me both of them. Oh, okay. So now that I know they're 857 and 1142, that's easy. Then I could just say, okay, what's the twist from A to C? Well, from A to C is that torque A, 857.14 times its, wait, do I need the twist? I don't need the twist. They said, I wasn't paying attention. It asked for the maximum shear stress, the tau. Again, that's what it's asking for, not for twist. I can find the twist of both of them, and that would check my work to make sure I actually got the same answer. But they're asking us for tau, not for twist. So we said that's the torque times C, which in this case, the shaft, I assume they're telling us that somewhere. Oh, it has a diameter of 40, which is a radius of 20, which is 0.02 meters. And that's divided by J, which is like last time, pi over 2 times, well, the radius to the 4th. So since it's like last time, I'm just going to write down the answer to that. You end up with 68 in terms of the back of the book, you'd get 68.2 megapascals for that. If you repeat this from C to B, is that right? C to B? Yep. C to B, everything is the same, except for you just have a different torque, 1142.86. And you get 90.9, predictably more, just because the only thing that changed in that equation is the amount of torque. And so in the last problem, we basically just said, oh, that's the max. We didn't have to find all of them. We just picked the one that was the largest, but you can find the shear stress in each chunk of it if you want to. And I won't take the time to do it, but it is a good exercise to go back and find the twist of both of those individually and go, oh, look at that, they are equal. That's cool.
And the twist, TL over.
Yeah, that's right. TL over JG. And did they tell me enough information? No, they didn't tell me what it was made out of, so I wouldn't be able to find it because they didn't tell me what G is. No, that's not true. 1.2 L2 steel. So there's my G. No, they told me everything I need. Didn't see that. So you could actually find the twist there.
We do that.
Yeah.
We do that.
So let's see, what's that stuff called? L2 tool steel. We're in metric land. Recall hearing that one before. L2 tool steel. Oh, there it is. So I need the G value, which is that 75 right there. So it's 75 times 10 to the 9th pascals. So I know that. And so if I did want to know the twist from A to B, I say, okay, the torque, just like before, 857.14 times the length of it, and that length is 0.8 meters. So notice that's a length, not C. And that's divided by JG. The J hasn't changed. It's pi over 2 times 0.02 to the fourth. And notice I'm thinking meters. Everything here is meters, Newton meters, and so forth. So I'm being lazy, but I know it's going to work. And then this was 75 times 10 to the 9th pascals, which is newtons per square meter. Again, it's a good exercise. Twist should come out unitless because it's a radian measurement. So I should end up with nothings if I stuck all those units in there. So I've got 857 Newton meters times 0.8 newtons, 0.8 meters, 0.02 meters to the fourth, and then I've got meters, newtons per square meter for that 75. Punch all that in. I don't know the answer to this because I didn't do it ahead. It just times 0.8 divided by 5 times 2 divided by 0.02 raised to the fourth divided by 75 divided by 10 raised to the 9th. I got 0.0364. I'm actually glad you asked to do this just because this is kind of a good exercise. So what about from B to C? Well, I just have a different torque, 0.86. But then I also have a different length, it's 0.6. Does it make sense everything else on the bottom is identical? So in one sense, what I could have done is just check the numerators of both of those. Is 857.14 times 0.8 equal to 1142.86 times 0.6? In my case, because I have that all typed in, I could just go back and retype it, like type over the top of it really quick, since most of it is still there. And I'm hoping I'll get the same answer. If not, we got a problem. 1142.8 insert 6. I got 0.06. I got the same thing. Of course I did. Aha, yeah. Equal, of course. Brain okay?
So they're the same because it's just one gear, right? So they're both kind of rotated the same amount. But they're attached.
Yeah, they're exactly. And it's not so much that there's a gear, it's just they're attached in the middle. So it's like if I draw a line across it, don't they both have to go the same?
It's still kind of hard for me to wrap my brain around that all these like just constants are equal. I guess the fact that pi, like the radius is theirs, but it's like the fact that it comes out radius is kind of blowing my mind a little bit.
Yeah, it should. Let's go ahead and write that in really quick here just to kind of remind ourselves. This is Newton meters. This is meters. This is meters to the fourth. This is pascals, which is newtons per square meter, right? So let's see, let's stare at all that. So 2 of those meters go away with 2 of these meters. These 2 meters go away with these 2 meters. Newtons go away with newtons. Oh, look at that. There's no units left. Oh my God.
It feels like we're just plugging in like forces and lengths and then outspits a degree.
Yeah, outspits an angle. Crazy. Interesting. Okay. Take a look at your note sheet. Because we now have to look at something. There's kind of on the top right-hand corner of your note sheet that I just handed you, there's like a little table, and it looks like what I have up here. And this is kind of cool because whatever section we're on, I think 5.6. 5.6 says, well, what if it's not a circle? What if the shaft is not a circle? again, off the top of my head, I found myself thinking, I'm not sure I've seen that. I mean, I think about things that are spinning. It almost always seems like it is circular, but well, could it be a square? And by the way, there is some motivation for that because it makes sense if you slide a circle inside something it wants to spin, like you do have to glue it to something. If I put a square in there, does it make sense? There's like a positive lock there, like it can't spin now because you got a square in a square hole. It's like not going to spin unless it strips. So, could something be a triangular or square or even an elliptical shape? And for that matter, couldn't you just make some crazy weird shape? But notice what's going on here. This is we aren't going to really take any time to delve into the bowels of this. And part of that's because it's not in the book and so forth. But notice the two things we've been calculating up here. Like that's the two things we need to know. How much does something twist and how much shear stress does that put on it? Again, that's how much do the washers want to slide past each other. Notice it's like a totally different formula. Like twist was twist was TL. Okay, I'm good with that. And then JG, but then there's a G, but there's no J, and then there's a 7.10 up there. Does it feel to you, this is what it feels like to me, it feels almost like somebody experimented with this and like found a constant to get this to work. And then of course, remember that pi over 2 c to the fourth was entirely based on the circular resistance to twisting that shape has. And so this is like not that anymore. This isn't a circle. And so notice this is kind of saying, well, it's a to the fourth. It's like whatever the dimension of the square is, it's like that to the fourth now somehow. So it's like a totally different version of J, because it's like, how do squares resist torsioning, twisting? How do squares resist that? How do triangles resist that? So do you see how these formulas kind of have something in common? Like it's the same exact formula, except for there's like a 46. It's like 46 more times more powerful. You get, well, actually, it's like less powerful because you get way more twist, right? If you say 46, like a triangle is going to twist more. Does it feel like a triangle wouldn't resist twisting as well as a square? It actually kind of does to me. And notice how many times does 7 go into 46? Like 6 times or so. It's like 6 times wimpier. It's going to twist a lot more. What about this last one? Whoa. That's ellipse is a special kind of circle. It's like a circle with 2 radiuses. Good news, I didn't assign any ellipse problems. That's kind of a weird shape. So let's just look at these first two. And then look at the tau formula, the shear stress formula. Remember how that was a second ago? That was like TC over J. What is it here? Well, there's still a T, but then the J, the resistance of that, it's the same thing. It's that resistance shape. It's like, well, that's now A cubed somehow. It's again, I find it weird personally. It's like, oh, I thought J must be A to the fourth, but then it is an A to the fourth over here. So it's not like that's actually just what J is. You see what I'm saying? So the point is they have some things in common. Like this is, for whatever reason, this is T over A cubed. This is T over A cubed as well, but they just have different multipliers. So I'm going to be asked the same questions in this section. It's not going to have a circular shaft. So I'll be using these formulas instead. Let's see if we can score a sample problem. With respect to the statement that I kind of made up here at the top to kind of just help you understand that, they support less shear stress and their twist will actually be more because it's less of a symmetrical shape. Does it make sense in the case of a circle? Like all the pieces around the outside edge of this are all kind of working together. They're all working equally to share against that. But does it make sense the dudes in the corner of a square aren't really helping much? Can you picture that? I got a square like this and I put some kind of a torque on it that wants to twist like that. Does it kind of make sense that all the stuff inside here is doing all the work? Like that guy out there in the end, he's not doing anything. Can you kind of picture that? Because isn't like this chunk right here pushing against this chunk right here, which is pushing against that chunk right there? What's that guy out there doing? Like he's not touching anybody. Like no neighbors are pushing on him. If you push me to this direction, I'm going to go that direction unless there's another dude that I push against. And then he's going to go that direction unless there's some other dude over there that he's pushing against. So it's like those dudes on the corners aren't doing anything. See what I mean?
Like outside the book thinking, but like if you're grabbing square, aren't you gonna grab corners for the most part?
Well,
The corners are going to shear off and then
yeah, I see what you're getting at
because
there.
in my head, I'm like, oh, those corners are going to receive the brunt of it, and then they'll shear, and then.
Well, you're thinking of it in terms of how it gets gripped.
Yeah, exactly.
But if the square slid into a square shaped hole, it wouldn't
Right,
behave
okay.
that way.
100%. Just for size purposes.
Mhm. And of course, however you grab the ends, if you kind of go like this to it, the inner part doesn't know it's being grabbed. And by the way, that's St. Venant's principle. In other words, when you grab the ends and tweak on them, weird stuff happens right around there because of how you grabbed it. But as soon as you get a little ways away from it, then it starts to even out. That's St. Venant's principle. And that's so what you said is the thing. That's a really good point. And then along the lines of the logic that I just made, does it make sense? All this stuff out here, there's like lots, like that's even worse. Like none of those guys are doing anything. Does it kind of feel like, these people inside here are sort of doing all the work? That's kind of what's going on. So anyway, that's interesting. Well, let's take a look at first a triangle. And this is a pretty interesting question. So let's see if we can tackle it. So, okay, here we are. Before we read the question, it's like, oh, there's this 4-foot triangular deal sticking out. And I notice it's an equilateral triangle because it's 60 degrees. So it'd be 60, 60, 60. So it's equilateral, which actually was important a second ago because that formula we had was for an equilateral triangle, wasn't for a right triangle. So it's like, oh, it's a good thing that's equilateral. So all the sides are 1.5 and it's 4 feet long. So that's not to scale. And so now someone's going to twist on it out there. And we're just going to wonder, well, how much shear stress does that put on that triangle? Is it going to break? And then how many radians is it going to twist? And so it's like, okay, I got formulas for that stuff. That's not bad. So let's see what was. And so this is a little different because it's told, I'm told that I'm using 2014 T6 aluminum and it's an equilateral triangle. This time though, it's the opposite. Notice it says determine the largest torque it can handle if the allowable shear stress is 8,000 PSI. That's just the reverse. So that'd be kind of like if I was using the questions a second ago, or using the equation a second ago when we said it was T times C divided by J. And we said, oh yeah, we know what torque is. Well, here we're saying we know this is 8,000 and we don't know what that is. And so this is like putting a limit on something like, hey, don't turn that wrench any harder than this, or it's going to break off. Have you ever torqued a screw off, putting a screw in with a cordless drill? The weak sheetrock ones, those little skinny black ones, sometimes those will spin right off. That's what we're talking about right here. Couldn't handle it. So the only difference is our formula is not quite like that because it's not a circle anymore, right? What's the formula for that? Oh, it was, let's see. Tau, yeah. Tau for a triangle. Maybe I'll put a triangle down there is 20T over A cubed. So it's like a slightly different formula. Oh, okay, so no problem. So this is 8,000 and notice I changed it to, and because I'm in unit land I'm not familiar with, I'm going to say pounds per square inch here because that's KSI. So that means the other side also needs to be in pounds per square inch. So let's see, torque. I would think that torque then would be foot-pounds. And A is in inches, so this is going to be cubic inches. Does it make sense that's not working? So would it work if it was foot inches? Oh yeah, it would work then, because the inches would cancel and I'd have feet on the top and square inches on the bottom. So I need T to be foot inches. Or I got to change 8,000 to I guess I can't even really do it. It's like I got to change A cubed to be feet cubed or something like that. So just knowing that T is going to come out in foot inches, maybe because I'm just solving for T, maybe that's not so hard. Okay, so A is in inches. I put 1.5 in there. Oh, okay, 20 times T divided by 1.5 cubed equals 8,000. Oh, that's not hard to solve. Just solve for T. Wait, foot inches. I screwed that up. I said foot pounds a minute ago and I got rid of pounds. I should have got rid of feet. inch pounds, right? Sorry about that. You guys should have told me I was being dumb. So yeah, now the inches would cancel. So I'd have pounds per square inch. Awesome. So I just need to take 8,000 times 1.5 cubed, divide by 20, and I'm going to get inch pounds for my answer. And there's nothing, didn't say I had to answer any certain way, so. Cool. Oops, sorry, I looked at the wrong one.
Oh, okay.
Yeah, 1350.
I like.
Now, what does it go on to ask? Notice that this time it gave us an allowable shear stress of 8,000, but then it went on and said there's even a limitation on the angle of twist. In other words, we don't want this thing twisting more than 0.02 radians. Well, isn't there a formula for that too? Again, I'm stealing this off that sheet. So isn't the angle of twist, seems like time to change colors, isn't the angle of twist equal to 46t times the length divided by a to the fourth, and then g, is it g? It's the formula, right? So, all right, I was told this has got to be limited to 0.02. And that's radian. So I need this to be unitless. Again, I'm a little concerned about this. So for length, I could put in 4 feet or 48 inches. I'm not really sure. I'm remembering G was in pounds per square inch. And so I think I'm going to put 48 inches in here for the length instead of 4 feet. Let's see if that works out okay. A is the distance along the side, which is 1.5. So that's just 1.5 to the fourth instead of 1.5 to the third. And that's inches. So it'll be inches to the fourth. And if I look up G for 2014 T6 and I look in the non-metric top portion of this, it's the very top answer. I'm getting 3.9. 10 to the third kilo. So that's actually 3.9, 10 to the sixth PSI. You agree with that? And so torque then, let's see, I got pounds on the bottom. So I guess torque is going to be inch pounds again, since I got all these inches. So does that all work out to unitless again, like I did a minute ago? Let's see, I've got 2 inches there, gets rid of 2 inches here. Then I've got 2 inches on the top, 2 inches on the bottom. I got pounds on the top, pounds on the bottom. Sweet. Yeah, that's actually unitless, so that's going to work. Remember though, I canceled, I'm probably going to erase what I just did, but I got rid of the units, but that doesn't mean 1.5 is still not to the fourth power. The inches is not to the fourth power. It's gone, but that's still 1.5 to the fourth power. Sweet, solve for T. This is what I wrote down a second ago. T comes out to be 178.8 inch pounds. But they actually ask a wonderful question here about this. They didn't just say calculate them. They said determine the largest torque T that can be applied. We found 2 different answers to it. If twist is the limiting factor, then you can only have 178 inch pounds. If shear stress is the limit, then 1350 is okay. Which one do I pick? I'm gonna pick that one. I'm gonna pick the smallest one. Does it make sense if I chose 1350, then it's gonna twist too much? Well, it won't snap, it'll just twist too much. The 1350 is the snap. It's the shear stress that snaps it. They just said, I don't want it twisted more than 0.02. So if I went over to here and I stuck in 1350 for that, I'm just gonna get a twist that's 0.07 or 1.2 or something like that, and it'll just twist. So I don't know why they said it can't twist that much. Is it ruin something in the machine? They just said they didn't want it to. Okay, well then you got a way smaller torque now. You're gonna have to go way smaller on the torque. So does it make sense that this ends up as kind of the limiting factor, if you will? And again, I like this question because it's just kind of saying, you know, somebody made something and now you go tell them, don't lift more than this or you'll break it, right? It's like driving across a bridge and it says 60,000 pound weight limit. The idea is don't drive across this if you weigh more than that. Bad things are going to happen. Now, I added my own question to the bottom. What if the same material was used, the same amount of metal? So do you agree there's a volume of metal there? It's 4 feet long and 1.5 by 1.5 by 1.5. And you might imagine somebody made that by, you know, melting metal and then pouring it into a mold. But what if you poured it into a cylinder? So it's the same exact amount of steel. How's it going to behave then if I use the same exact amount of steel?
Well, yes, but I think the same way.
So let's at least do part of this. So in the interest of time, like we're gonna still keep it 4 feet long. And I said that here, the same length. So let's figure out the area of that triangle right there. Area of a triangle is base times height. The base is 1.5. The height, though, I don't know. I got to figure that out. Since all the sides of this are 1.5, does it make sense that's a right triangle in there? So I could say let's see, that would be the tangent of 60. No, the sine of 60.
Yeah. Yes, I'm 60.
Sine of 60. Yeah. Sine of 60 equals the height divided by 1.5. So 1.5 times the sine of 60. I'm in degree mode.
The radius is going to be bigger and you're going to have a factor of 48 or 46 when you do the angle.
So the height's about 1.3. So I can say, oh, this is 1.5. Area of a triangle is base times height times a half. I forgot the half earlier. So it's 1/2 times 1.5 for the base times the height of 1.3. So I get an area of 0.974 approximately. And that'd be square inches. So see, now what do I want to do? I want to design a circle with the same exact area. That's exactly right. Pi radius squared, and I know I want that still to be 0.974. And so what radius would that be? So notice if I divide by pi and take the square root, algebraically, I get 0.557.
That's also your C. Going to your thing.
That's your C. That's right. That's exactly right. So now I know what size circle this would make if I poured it into that kind of a mold. And so, okay, great. Let's go find the twist. Let's go do the twist thing. Now, remember, this is back to a circular shaft. So we have a different formula for this now. So I'll write it out. Your twist was equal to the torque times times the length. I'm going to write all the letters in this time and we'll replace them. Torque times length divided by J times G. And so we said this has got to be 0.02. We said we don't know what the torque is. We're going to calculate that. We said the length is 48 inches. J is different because it was pi over 2 times the radius, as Caesar just said. I'm leaving the units off. I'm just making sure everything is in inches. So that's to the 4th. And then we said G. G hasn't changed, right? It's still 3.9 times 10 to the 6th. So solve that for T. Cool. If you don't screw that up, you get 245.5 around there.
And what a 60% increase.
Yeah, elaborate on what you just said there. Increase, what are you talking about?
The force taken line. You get that angle.
Yeah, do you see the connection between these two guys right here? This is what Caesar's referring to. When it was a triangle, we said, oh, don't do more than 179. You put more than that torque on it, it's gonna snap. What happens if you make a better shape out of it? What if you don't waste those corners? Oh, 60% increase was what Caesar either calculated or estimated. Way more force. Like that's why they're circles. You see what I mean? It's like the same use of steel. This triangle guy just made it stupid. He made it weak. Interesting. Does make me wonder about the gear thing, you know, how you have, because you do have, as I said, you have issues with sometimes stuff needs to slide into other stuff, and they've got, you know, the splined gear that slides into something to get it to turn, and that's really cool because it can come in and come out, and you might need it to be able to move, or you need to be able to replace it, so you can't just weld it or whatever. Maybe there's some reason for that. So, you know, again, that kind of makes me wonder. Now the shape is a star. That outer shape is not a circle, but it's a star in that spot right there. And so do you treat it like a circle and just pretend all the teeth are gone because they're doing nothing? Do you just ignore the teeth that are there? You know, is there some crazy formula like we've just been studying, but even worse for something that looks like that?
You're talking about teeth snapping, use like these.
Yeah, it's kind of like, I mean, it looks kind of like a sun.
If you have a pitch outer and
Pitch diameter. How the heck do you know that? You're not supposed to know that.
big manufacturing.
Yeah, it's pretty cool stuff, isn't it? Yeah, gears and how they're round and they can get those to actually roll past each other and not, you know, grind into each other. It's really cool. Yeah, something like that. In other words, is there some formula for that shape? It's not a triangle or a square. Or do you just kind of say, oh, those teeth out there, you know, are kind of not doing anything, so I'll treat it as a smaller radius circle and then I get nothing for the teeth? I don't know the answer to that. That's kind of a good question, isn't it? But you can appreciate if I slide that into something, then it's going to want to turn whatever I put it into without having it be glued or screwed or welded or whatever. Yeah, that's exactly right. Can't the teeth shear off? That's an issue too, isn't it? And that happens. So that's kind of interesting.
You ever have those screwdrivers that are like off the head instead of the Phillips? Those things are awesome.
Yeah, the star point.
Yeah, sorry.
Yeah.
I literally wish
Torques. Yeah.
that everything, I converted my house to all like,
So did I.
you know, but like when you buy something and it's like, oh, Phillips. I
Yeah.
want to use the Phillips.
Yeah, those are dumb. I totally agree.
They never strip, so like, I would really agree.
Okay, let's do just one other one with a square. This won't hurt you because it's the same, just a different set of formulas. But let's take a look at this one.
You still-
Notice this time, though, they didn't ask us to kind of calculate the maximum torque. They asked us the more normal question. They just said, cool. Go put the torque on it that shows. Notice it's got 20, 60, and an 80 on it, right? 20, it's like giving us the torques, and it's just saying, great, tell us how much shear stress is in it. Okay, I can do that. Shear stress. What's the formula for shear stress? And it's max, it's the constant 481 times the torque divided by the size of the side to the third power, right? And so everything, these lengths are in meters. I'm thinking I'm going to call that 0.25 there. I'm going to call it 0.025 meters. I'm going to put that in for this. .81 is a constant. And then let's see torque. So since the shear has got to be in newtons per square meter, that kind of makes sense then that this torque right here would be in Newton meters, because it would cancel, the meters would cancel with one of the meters, and then I'd have newtons per square meter. Okay, so that's cool. Now, they did not say, let's find all the different shear stresses. They said, let's find the biggest one. Again, that makes sense, doesn't it? What's the biggest torque? Well, notice there's a 20 here. So everything in here is 20, 20, 20, 20, 20, 20, 20, all the way across, right? What happens when you hit the 60? Notice it's going the same exact direction. So it's 20, it's 60 more than that. So this would be 80. And that actually agrees with what's over here. So I basically have a 20 and an 80. Oh, I'll use the 80 then. So I just need the max. Again, I don't think that's necessarily obvious. Again, what are we looking at? We're not looking at 20, 60, and 80 as though those are the three answers to choose from. Had you done that, you would have got lucky here. You would have chose 80 and you would have got lucky. But again, I highlight that because I found that hard to make sense of for a while. You really have to think of the section thing. Now it's 20 all the way across. Oh, okay, sweet. So then and notice the units are already right. It's like 80 Newton meters. Oh, cool. 4.81 times 80 divided by 0.025 to the third. Cool. In my case, because I got newtons per square meter, I got some giant Pascal number, and you can appreciate that's probably 24.6 megapascals in the back of the book. Cool. Now I can choose material. Oh, interesting. They already chose it for me. I hope they did good. Right? What about twist? Completely different formula for twist. Twist. Twist for a square, 7.1 times T times L, a to the fourth G. Whew, that's a lot going on. I already forgot what it was. T, the torque. Dumb. How did you not know it was torque?
And you just get the torque and the length and find out which of the two is bigger and then use that as the max.
Yeah, this is an interesting one. So let's just start throwing a few things in. I can see the length. I can see the length of this is, well, now I'm a little confused because is it 2 meters?
Oh, it's the overall.
Or is it 1.5 or is it 0.5? Okay, so let's wimp out a little bit here. Let's stall. It's always a good tactic. Is 0.025 meters. G. Oh, that's why they told me it was 6061 T6 aluminum. I have to look G up. In the interest of time to get you out of here, that's 26 times 10 to the 9th. Mega or gigapascals. So that's pascals. But I'm a little confused by the torque and the length because I've got the 3 torques, well, maybe 2. I got 80 and 20.
You can't use the overall length because your torque is 0, isn't it?
What's your thoughts on what Caesar just said?
Cancels now.
Gotta pick C to B or B to A.
B to A. C to B is moving the same direction.
He's exactly right. The torque is 0 if you do the whole length. So that makes me think then the length isn't 2 meters, right? So now all of a sudden I feel like I have to pick one, right? Well, we did that before. Didn't we pick the we're trying to find the maximum shear stress.
The bigger ones they do, the length times the torque on that is greater than the length of the torque on DC. So that's the maximum. To be the one.
And I sort of purposely made this a little confusing because of the way that I said it, just to make you think. But the answer to this is you need the total twist. In other words, this is the twist from A to C, which means you have 2 problems here.
Ah.
But that's what we did before, didn't
We
we?
get rid of the 7.1, the 80 and these, because you go to the other. Oh, no, never mind.
Yeah, it's not 0. Yeah, it's not pinned this time. This is kind of back to just a normal shaft. This is actually way back in like 5.3 or something now. It's 5.3 with a different formula. So I've actually got to add those 2 things together. And so I have a 20 torque, and that was in the 1.5 meter area. And I have an 80 torque, and that was in the 0.5 length area. I got to add all that stuff up. Again, not obvious. I can't remember if I got this wrong the first time, but you know, the temptation to just say, oh, it's all the way across. But remember, twist is torque and length. Like it makes sense why you'd have to do both of these separate, because the twist of those 2 is not the same. And because it's not pinned on either side, the twist from A to C is found by adding up both chunks individually. So if you don't screw this up from A to C, you get 0.0489. So unlike the last one, this calculation is just hoping for the best. It's like they pick the steel, they put the torque on it. It's like, oh, I hope it doesn't break. I hope that didn't twist too much.
That's when we look at our previous note sheet with the graph of the point of no return. That's something like this.
Yeah, I don't. This is really 5.3, if I remember right. 5 point, no, maybe, no, it was 5.4. 5.4 was twist. This is,
Well, like we have our sigma, if we go past a certain stress, then the whole
Right.
thing is gonna not return.
I
back to
gotcha.
its-
Yeah,
So then if this twist is too much, it's not gonna. twist
yeah.
back.
And that's where these limitations would come from, because usually you'd say, I want this material to stay in the elastic region, which basically means when I let go, it goes back to normal. If you get beyond that, then it doesn't go all the way back to normal. And that is something we're actually going to tackle later, is like, what if you do take it past that, and then where is it going to end up? How many radians will it be when you let go, if you went past that elastic region? Elastic again, you know, it makes sense, like underwear. Let's have them go back. Yeah, so I'll say this sort of this harkens to the questions that we did last time we were together in 5.4, where we actually did have to add them when the ends weren't pinned together. So So we'll do this next time because I want to shut up and let you get out of here, but just to show you, like, one of the other options you have is, what about a shape like this that's not square? And not only that, it's hollow. But you can appreciate that's not an uncommon thing to have a hollow piece of steel or something like that and have there be torsional motion on it and so forth. So it's like, how's that gonna work? How's that thing gonna behave when it's under load? I mean, is it possible to find the amount of shear stress that's on that too? Because it's just material. If I twist it, it's gonna try to twist, snap off. I will note in the, actually, I don't think I have the updated note sheet on here, but we'll talk about it next time. But the formula for that is the next thing that's on the note sheet. And it's a very interesting, surprising kind of a formula because it's hollow. It's like, how's that thing going to behave? Because all that stuff in the middle is missing. Every other time this has been solid. And so if there's nothing in there, it's like, that seems like that's important. Does it make sense that the outer stuff is doing more of the work though? So if I have a hollow pipe, all that outer material, I mean, if I have a certain amount of material like we did a minute ago and I made a hollow pipe, that's actually going to not want to twist near as much as if it got way smaller and it was a solid pipe. Because again, it's about distance away. The further it is away from the center, the more it does not want to twist.
You're saying replace a denser, smaller pipe with a hollow, bigger.
Exactly, yeah. Yeah,
Which
which you weren't here for this, Connor, but that's exactly the same principle with that. If you, in an I-beam, this distance from here to there is really far. Those top members, that upper member up there, when you put it under pressure from the top, it's going to want to compress. But in order, that top one is going to want to compress a lot way up there, whereas the middle stuff, I talked about this in chapter 6, the middle stuff doesn't change length at all. So if you can get all your material way away from the center, then the bottom ones are going to want to pull apart. Well, for that really long, the bottom ones are going to have to pull way apart. They're not going to want to do that. So you want all your material far away. Same in circle. If you have a solid steel, it's only the size of my finger, but then you say, oh, let's melt it down and make like a pipe that's this big and it's hollow in the middle. This is going to want to twist way easier than this will, because all that material way on the outside is going to have to twist further, and it's not going to want to do that. So it's kind of a cool concept. But it's a different formula and we're out of time. Let's tackle that next time.